Time doesn't move at the same rate everywhere in the universe, and that's not a metaphor. Somewhere out there, it flows in a way so extreme that it would bend our very understanding of reality. We call that place a black hole, and it's not just a cosmic destroyer, it might also be the most tantalizing promise we've ever stumbled upon. So, if I told you there's a place where time rushes so fast that the future is already waiting for you, would you believe me? We take it as a given that time is the same for everyone, ticking away at a steady, universal rate. But over a century ago, Albert Einstein published his general theory of relativity, turning that simple assumption on its head and revealing a reality far stranger than we ever imagined. The theory, unveiled in 1915, made a truly radical prediction. Gravity isn't just a force pulling objects together, it's actually the warping of space and time itself. To picture this, imagine a large, tight rubber sheet stretched out flat. Now drop a heavy bowling ball into the center of it. The fabric dips and curves, creating a deep indentation around the ball. This curved sheet is our four-dimensional space-time, and the bowling ball is a massive object like a planet or a star. Any smaller object rolling near that indentation would naturally follow the curve of the fabric, spiraling inward, much like the moon orbits the Earth. Now here is the part that shatters our everyday intuition, the part that Einstein's theory revealed. The rubber sheet isn't just space. It is not just a map of where things are. It represents time as well. The more massive the object, the deeper the dent, and the more it distorts the very fabric of time itself. You see, these two are not separate, they are woven together. What we experience as time is just as much a part of this geometrical fabric as the three dimensions of space. This brings us to the mind-bending conclusion that you need to hold on to for the rest of this journey. The object causing the dent isn't just bending space, it is actively slowing down the flow of time around itself. The gravitational pull an object exerts is, in this sense, a measure of how much it is curving the path that time takes. The stronger the gravity, the slower time moves, relative to somewhere the gravity is weaker. So, the ground beneath your feet is traveling through time slower than the air above your head, even if by an unbelievably tiny margin. The universe is a stage made of something that we can bend, twist, and distort, and the clock inside that distorting influence is ticking at a different rate. But here is the crucial question that separates a wild idea from a true theory. Can we actually prove that time behaves like this? How can we ever test something so far removed from our daily experience? Because this isn't just an abstract philosophical idea, it seems so utterly majestic and detached from our lives. The effects are happening all around us, all the time, in ways that are measurable. So how do we know that this is actually true? The year is 1959, and a physicist at Harvard University is about to prove something that sounds like pure science fiction. Robert Pound and his graduate student Glenn Rebka set up an experiment in the university's Jefferson Tower, a brick building that stands over 70 feet tall. They placed a radioactive sample of iron at the bottom of the tower and a detector at the top, then measured the frequency of photons traveling upward against gravity. The results confirmed that time itself moves faster at the top of that tower than it does at the bottom, a difference so small it only shows up as a tiny shift in the energy of the particles. Over that modest height of just 22.6 meters, the flow of time was measurably different, and the findings were published in physical review letters. But that was only the beginning, because a decade later, scientists decided to take this test all the way around the planet. In 1971, Joseph Hafey and Richard Keating packed 4 atomic clocks made of cesium onto commercial airliners and flew them around the world, once heading east and once heading west, while identical clocks stayed behind at the US Naval Observatory. When the planes landed, the comparison was staggering, even though the numbers were almost impossibly small. The clocks that flew eastward came back about 59 nanoseconds slower than the ones left on the ground, and the uncertainty in that measurement was just plus or minus 10 nanoseconds. That tiny fraction of a second, less than the blink of an eye, was the physical proof that motion and gravity both warp the passage of time. Think about that for a second. We are not talking about some far-off galaxy or a hypothetical experiment in a laboratory of perfect conditions. This was 4 clocks on ordinary passenger flights in the year 1971, and the difference was measured with such precision that it matched the predictions of Einstein's theory almost exactly. It tells us that the ground beneath your feet is moving through time at a slightly different rate than the roof over your head. It means that if you live in a penthouse, you are aging just a little bit faster than someone in the basement, even if the difference is far too small for any human body to feel. But here is the punchline, the one that leaves you staring at the wall. If time can bend by a measurable amount across a single tower and a single plane ride, then what happens when you stand next to an object with the mass of 1,000,000 suns? That is not a rhetorical question, and the answer is so extreme that it breaks your intuition into pieces. Before we get there, let me ask you this. Have you ever felt like time is slipping away from you? Like the seconds are not quite what they seem? Maybe you are not wrong. On Earth, the effect is laughably tiny, but it is real, and it has been real since 1959. And that is the whole point, because if such a small difference in gravity can mess with time, then there is a place out there where the difference is not small at all. A place where time does not just slow down, it practically stops. We will go there soon, but first you need to understand how those 4 clocks on a plane changed everything we know about the universe. The Jefferson Tower experiment is the kind of story that sounds too clean to be true. 2 men, a brick tower, and a gamma-ray source. Yet it worked because they were willing to doubt one of the most basic assumptions we all carry around in our heads. Most of us assume that a second is a second, no matter where you are. Pound and Rebka proved that a second at the bottom of a tower is not identical to a second at the top. The photon that traveled upward lost a tiny amount of energy, not because it slowed down, but because time itself was flowing faster up there. Every single atom in your body is ticking to a rhythm that depends on where you stand, and that rhythm shifts when you climb a single flight of stairs. And here is the thing that really made the Haffaley-Keating experiment so decisive. It did not just measure one effect, it measured both of them together. The clocks flying east moved faster relative to the ground, which slows time down, but they also flew at a higher altitude, which speeds time up. The 59 nanoseconds they ended up losing was the final score after those 2 effects fought it out. That kind of messy, real-world result is exactly what makes it convincing, because it shows that the theory is not just a neat equation on a blackboard. It is a description of how the universe actually behaves when you put your equipment on a commercial flight and let the numbers land wherever they land. So the next time you hear people say that time is a human invention, remember those 4 clocks. Remember that they returned from their trip around the world, carrying evidence that the universe does not care about your wristwatch. And then ask yourself, if a change in altitude of 30,000 feet can steal a few billionths of a second, what would happen if you could approach a rim of space-time where gravity is a billion times stronger? That is what we are heading into now. The clocks have already told us the truth, and the truth is that the future is not waiting for us somewhere out there. It is already being written at different speeds all around us, and at the edge of a black hole, it is being written in strokes of fire. A black hole is not a vacuum cleaner. If you replaced our sun with a black hole of exactly the same mass, Earth would keep orbiting it perfectly, untouched, because gravity only cares about mass and distance, not what the matter looks like. This is the first twist that breaks your intuition. A black hole is not a cosmic monster that devours everything around it. It is something far stranger, a region where space-time itself is bent so severely that the usual rules of the universe stop applying. And at the very edge of that region sits a boundary with a name that sounds almost poetic, the event horizon. The event horizon is not a physical surface you could touch or stand on. It is a mathematical line, an invisible point of no return. Once anything crosses that line, even light itself cannot escape, which means everything happening inside is permanently hidden from the rest of the universe. That is the law. Nothing that goes in ever comes out, and no signal, no image, no whisper of information can travel back across that threshold. So what does this mean for someone watching from a safe distance? If you saw a friend falling toward a black hole, you would never actually see them reach the horizon. They would appear to slow down, hover, and then freeze in time, their image fading into darkness as the light from their body stretches and dies. But here is the part that should make your stomach drop. For your friend, time keeps moving normally, and they would cross that invisible line without ever noticing the exact moment they passed it. The boundary is not a wall, it is a trap that closes behind you silently. And once you are inside, the universe outside becomes a memory you can look at but never return to. What truly happens to their clock, and to the time they experience when they finally step into that frozen frame. So, what would you actually see if you watched an astronaut fall into a black hole from a safe distance? You might expect a quick disappearance, a final scream, and then nothing. But the universe has a far stranger, more mind-bending fate in store. The mathematics of a non-spinning Schwarzschild black hole reveals that the time dilation factor at the event horizon doesn't just get large, it blows up to infinity. For us, watching from Earth, the astronaut's descent would appear to slow down, gradually grinding to a halt right at that invisible boundary. We would never, for all of eternity, witness them actually cross the line. This is where your intuition takes a complete nosedive. The light reflecting off their spacesuit wouldn't just dim. It would experience an infinite gravitational redshift, as described by the American Physical Society. Every photon would lose all its energy, shifting to longer and longer wavelengths until it fades into complete invisibility. The astronaut isn't just frozen in time. They are literally erased from our observable universe. their image hanging on the edge of the horizon like a permanent ghostly photograph. We see the story pause forever, a single frame in our view of the cosmos. Yet here is the truly mind-shattering twist that breaks your brain. From the astronaut's own perspective, absolutely nothing special happens at that boundary. They feel no terrible force, they see no dramatic flash of light. Time for them flows just as normally as it does for you reading this sentence. They would float right through the mathematical surface, completely unaware that they've just crossed a point of no return. The profound, almost insane conclusion is that the story of their fall isn't paused for them. It's only paused for us. Our universe ends their timeline, but their own continues into a realm we are fundamentally incapable of seeing. You remember that scene in Interstellar where they land on Miller's planet, and by the time they get back to the ship, 23 years have passed for the crew member left behind? That moment, when Cooper watches decades of video messages from his children, is one of the most emotionally devastating scenes in modern cinema. But here's the thing that makes it even better. It's not just a clever sci-fi invention. The physics behind that planet is real, and the ratio they used was a staggering 1 hour on that world equals 7 years back on Earth. That's a time dilation factor of over 60,000, meaning time itself was flowing 60,000 times slower near that planet's surface. The science consultant for that film was Kip Thorne, a Nobel Prize-winning physicist who spent years making sure every equation on screen was defensible. Thorne confirmed that the 1 hour to 7 years ratio is entirely possible within the laws of general relativity, but it demands something very specific. The black hole in the film, named Gargantua, isn't just any black hole, it's an extremely rapidly rotating one, what physicists call a Kerr black hole. This kind of black hole drags space itself around with it, creating a region where stable orbits can exist much closer to the event horizon than around a non-rotating black hole. You see, around a Schwarzschild black hole, the one that doesn't spin, the math we talked about earlier kicks in brutally, and your time dilation factor just keeps climbing to infinity, making a stable orbit with a steady ratio impossible. But Gargantua's spin changes everything, allowing for a scenario that makes the impossible seem almost routine. So the next time you watch that scene, know that you're not just watching a movie, you're watching a masterclass in applied physics, where the most advanced equations in science were bent into a story about love and time. But that was fiction, carefully crafted to move us. Out there in the real universe, we've actually watched this phenomenon happening around a genuine supermassive black hole. Let's look at the center of our own galaxy. Want to see something that sounds like science fiction but is actually happening right now, 26,000 light-years away? At the very heart of our Milky Way galaxy sits a monster, a supermassive black hole called Sagittarius A, with a mass of 4.3 million suns, a reality confirmed by the European Southern Observatory. For 25 years, astronomer André Arguez has been watching the stars that orbit this beast, and one of them, a star named S2, has a front-row seat to the most extreme physics in our galaxy. In 2018, S2 made its closest approach, flying within 120 billion kilometers of the black hole at a blistering 7,654 kilometers per second, about 2.5% of the speed of light. Now here is where it gets truly mind-bending. When Gez and her team at UCLA analyzed the light from that encounter, they found something incredible. Time itself was moving slower for S2 than it is for us. Not by much, just a tiny 0.3%, which is about 4 hours lost every 17 months. But here is the thing. That measurement, published in Science, marks the very first time we have ever detected gravitational time dilation around a supermassive black hole with a single star. We are not just talking about a theory anymore, we are watching it happen in real time. So, how do you even grasp the meaning of such a measurement? To put it in perspective, your GPS has to correct for the same fundamental effect every single day, because time flows ever so slightly faster for satellites than it does for us on the ground. This is the very fabric of our universe, shifting and stretching depending on where you are and how strong gravity is, and the fact that humans can measure these cosmic distortions across tens of thousands of light-years should leave you in awe. So, if we look even further out, at another giant black hole that we have actually managed to photograph, what will we find waiting for us? On April 10, 2019, the world saw something once considered impossible, the first photograph of a black hole. For decades, these cosmic enigmas were locked away in mathematical equations, invisible to every instrument we had. Then the Event Horizon Telescope collaboration, led by Shepard Dolaman, pulled back the curtain on the monster living at the heart of galaxy M87. But here's the twist that makes this achievement almost unbelievable. They weren't using one giant telescope. They linked 8 radio observatories across the planet into a single Earth-sized virtual eye. Then came the real torture. Those observatories gathered a staggering 5 petabytes of data, enough to hold 5,000 years of high-definition movies. And that data sat on hard drives, traveling by airplane, while supercomputers at the University of California, Berkeley, chewed on it for over 2 years before a single image emerged. What was the payoff for all that patience? Start with the scale. M87 doesn't just outweigh our Sun by a little. 6.5 billion times heavier, a size that made earlier models look laughably small. And its distance? The light captured in that historic photo left its source 55 million years ago. At that time, dinosaurs still ruled the Earth, and that ancient glow only reached our planet in 2019. Now look closer at the image. That dark void at the center, the famous shadow, spans a mind-bending 38 billion kilometers in diameter. It's fully 2,000 times larger than Earth's orbit around the Sun. That isn't the event horizon itself. It's the horizon magnified by gravitational lensing, stretched into a silhouette against the glowing gas swirling around it. Have you ever felt completely dwarfed? Because staring at that shadow is like staring into the abyss of all perspective. What could possibly be more terrifying than a void so large it swallows light itself? Nothing. Except perhaps the temperature of the matter spiraling around it, and that's where this story gets truly fierce. When matter spirals into a black hole, it doesn't just vanish silently into the dark. It forms what physicists call an accretion disk, a swirling maelstrom of gas and dust heated to unimaginable extremes. This disk can reach temperatures above 10 million Kelvin, which is roughly 1,000 times hotter than the surface of our Sun. At that heat, the material doesn't just glow. It screams across the universe in powerful X-rays that we can detect all the way back on Earth. So even though a black hole itself is invisible, its feeding frenzy creates a beacon that is impossible to ignore. Now let's talk about the most violent event our universe has ever witnessed. On September 14, 2015, the LIGO and Virgo detectors picked up a signal that lasted just 1/5 of a second. It was a chirp, a tiny blip in the data, but it represented the collision of 2 black holes, one with about 29 times the mass of our Sun and another with about 36. In that fleeting moment, they merged into a single black hole of 62 solar masses. Did you catch the math there? That means 3 entire suns worth of mass didn't become part of the new black hole. It was converted directly into energy, released as gravitational waves in less than 1 second. That energy output is so staggering that it defies comparison. For that brief moment, the power radiated was more than 50 times greater than the combined light of every single star in the entire observable universe. Every galaxy, every sun, every shining point in the cosmos, and this single collision outshone them all. It took the team at LIGO over 2 months of furious checking before they dared to tell the world. They had to rule out every possible source of interference, from passing helicopters to earthquakes, before they could believe their own instruments. Even Kip Thorne, one of the founders, was deeply skeptical of the result at first. That skepticism is what makes science so beautiful. The signal was so clean, so perfect, that it seemed too good to be true, an unwelcome gift that had to be tested from every angle. And when every test came back clean, the realization hit like a wave. Nature wasn't just destroying matter, it was converting it into the very fabric of space itself. The black hole isn't merely a cosmic vacuum cleaner as we once thought. It's the universe's most efficient engine for turning mass into raw, pure energy. But what happens to that space, to the very geometry of time, when you cross that deadly line? What happens to time and space once you cross that deadly threshold? A 2024 study from Harvard University's Center for Theoretical Physics suggests something so bizarre it feels like science fiction. From inside a black hole, time and space actually swap roles. Time becomes just another direction in space, while space itself becomes a one-way street, a forced march toward the singularity at the center. This isn't a choice an astronaut makes, it's a physical inevitability, as unavoidable as tomorrow's sunrise. Once you fall past the event horizon, moving toward the singularity isn't a decision, it's your future. Every path forward in this new reality leads deeper inward, and there's no turning back, no changing your mind. The very geometry of the universe has rewritten its own rules, turning what we think of as a location into a destination we're helpless to resist. It's the most profound trap imaginable, a prison built not from walls but from the fabric of existence itself. But if you were hoping for a gentle descent, you'd be sorely mistaken. According to NASA, falling into a black hole with the mass of 10 suns means your head and feet would experience a tidal force difference of roughly 100 million Gs, all within 100 kilometers of the horizon. That's enough to tear apart your atoms, stretching you out in a process scientists grimly call spaghettification. A 2024 simulation from the University of Colorado Boulder paints an even more graphic picture. An astronaut falling into a black hole would be pulled into a noodle-like strand thousands of kilometers long before ever reaching the event horizon. Yet here's the twist that might make you exhale with relief. A 2022 case study from the University of Texas at Austin, run on the Stampede 3 supercomputer, simulated a dive into M87, the supermassive black hole we saw photographed in 2019. With a mass of 6.5 billion suns, the tidal forces near its event horizon are far gentler than those of a small black hole. An astronaut could cross the boundary and survive for several hours by their own clock, experiencing a soft, almost dreamlike fall into the cosmic abyss before being torn apart near the singularity. It's a strange, haunting thought. The bigger the monster, the more peaceful its embrace. So, does all of this finally answer the question we started with? Is a black hole a time machine? Is a black hole a time machine? The honest answer is yes, but only in one direction, and it's a direction you might not expect. We're not talking about popping back to yesterday to fix a mistake. We're talking about a one-way ticket to the future. A future that arrives far sooner for everyone else than it does for you. A 2024 simulation from the University of Oxford paints a staggering picture. A crew could spend 10 years near a black hole and return to find that 1,000 years have elapsed on Earth. This isn't just a wild theory from a sci-fi movie. It's a direct consequence of the mind-bending physics we've been unpacking. This is the twin paradox, pushed to its absolute extreme. You've probably heard the version where one twin rockets off at near-light speed and comes back younger than the one who stayed home. A black hole does the exact same thing, but with a gravitational pull so immense it warps time itself. Spend a year orbiting close to that event horizon, and when you get back, decades might have silently slipped by for everyone you knew. But what about the past? That tantalizing dream of revisiting history or warning your younger self? This is where the physics gets truly unforgiving. The math allows for a theoretical loophole called a closed time-like curve, essentially a loop in spacetime that could, in theory, let you travel backwards. A 2020 study in Physical Review Letters even suggested such a curve might be possible in a hypothetical 5-dimensional universe as envisioned by string theory. But here's the catch. Even in that exotic scenario, it would violate causality, the fundamental principle of cause and effect. And when physicist Sabine Hossenfelder from the Frankfurt Institute weighed in back in 2019, she drove the point home. Hossenfelder argued that to create a true time machine, you'd need to spin a black hole faster than the Kerr limit, the maximum speed allowed by physics. Such a thing doesn't exist in nature, and trying to force it would require violating the basic laws of energy. So the verdict, at least according to modern physics, is brutally clear. You can't build a black hole time machine to go back. The universe, it seems, has set up a door that only swings one way. We've been given a path to the future, but the past is sealed off forever. And that brings us to the biggest questions about existence itself, and the mysteries we haven't yet cracked. So, you asked whether a black hole could ever be a time machine, and now you have the answer. You asked if I could show you a place where time flows so fast that the future is already waiting there for you. And now you know that the answer was yes all along. We began with a wild idea, and we traveled through Einstein's warped geometry, through the impossible boundary of the event horizon, past the frozen light of infalling matter, and into the heart of a supermassive giant where time itself trades places with space. We saw how a single hour on Miller's planet could cost 7 years back on Earth, how a star called S02 slows its own clock by a tiny fraction as it whips around our galactic center, and how the colossal shadow of M87 stretched across 38 billion kilometers of nothing. And if all of that still feels like science fiction, remember this. The GPS in your phone only works because engineers correct for the fact that atomic clocks on satellites tick 38 microseconds faster every single day than the ones on the ground. A direct, practical consequence of time dilation that you rely on without a second thought. But this is where the story turns strange in a new way, because there is a deeper mystery that even geniuses have not cracked. In 1976, Stephen Hawking proposed the black hole information paradox, a puzzle suggesting that anything falling into a black hole might have its information lost forever, which would break a sacred rule of quantum mechanics, and physicists have been fighting over it ever since. That same Hawking, 2 years earlier, had already predicted that black holes are not truly black, that they emit a faint thermal glow from quantum effects near the horizon, and that this radiation slowly drains their mass until they simply evaporate. A black hole the size of our sun would take about 10 to the 67 years to vanish completely, a number so absurdly large that it dwarfs the current age of the universe by a factor of a billion times over. So, what does all of this mean for you, standing here on Earth with your ordinary clocks and your ordinary worries? It means that time is not a stage we sit on, but a fabric we are woven into, bendable, stretchable, and absolutely real in its consequences, which makes the final question not about black holes at all. If time itself can be distorted so violently, if the universe can hold places where the future waits ahead like a destination, Then what does that say about the few short decades you have been given? And what will you choose to do with a gift that, for all you know, is the only one you will ever get?